18. Page 18. Page 18. Let me review some values here. So we're going to do derivatives. Let me see what this we do. Yeah, we might as well cover trig as well. All right. So we're talking about e to the x, natural log of x, sine and cosine. We're doing a little bit of trig today, and then we'll finish some of the other trigs later on. So we did power rule. Power rule is the most used, or the derivative rule that's going to show up more often than any others. But these are also really close in terms of the amount of times you're going to see it on the AP exam. So e to the x, natural log, sine, and cosine, these are very commonly represented functions on the AP exam. So there's kind of a bit of a hierarchy in terms of, we're going to learn all these different functions. We're going to learn all these derivatives, but we kind of have an idea of what they're going to focus on and what functions have less likelihood of showing up on the AP exam. We're going to touch on everything that we need to know, but it's just good to know, what ones to focus on and which ones that we, can maybe, if we don't want to memorize it, we can take a chance on not memorizing some of the ones that have lesser chance of showing up. But these are guaranteed. Okay? So power rule, e to the x, natural log, sine, and cosine. These are probably amongst them. These are the 5 most commonly referenced functions on the AP exam. So here are some helpful values. Natural log of 1. Anyone know what natural log of 1 is equal to? 0. Yeah. What about natural log of 0? Undefined. Yeah. If you think about your natural log graph looks like this. There's a vertical asymptote at the y-axis, and the graph goes through 1, 0, and it goes through e, comma 1. So I memorize, or having just those 3 pieces of information can really help us approximate values on a natural log function. And these are also just important values that we should know. So let me add one more here. Natural log of e is equal to 1. And just think of these as, order pairs or non-order pairs on e to the x graph. E to the 0, what does that equal to? 1, right? Anything raised to the 0 power is 1. And these two, the last two here, highlights the inverse relationships between exponentials and logs. If I insert an inverse into the function, or if I insert a function into its inverse, they're going to have a way of canceling each other out. And so if I have e raised to the natural log of a, this is just going to reduce down to be a. So e and natural log cancels out. I'm only left with that a. Same here. If I have natural log of e to the a, natural log and exponential cancels out. All I'm left with is that exponent. These rules, these derivative rules are going to get a lot more complex in terms of, but we're just going to basically learn the very starting points of these, and then we can build on these derivatives as we get to like chain rule in our next unit. So exponential function, the derivative formula for exponential functions. So again, a derivative is describing the slope behavior of my original graph. And the beauty of e to the x is that the e to the x function itself describes the slope behavior of the function. This is very unique. So if I look at e to the x, the y value, so e to the x not only describes the location of the y value, it also describes the slope at that point. So basically, the function and the derivative are the same. So here you can imagine this, this is as a y value of maybe like 0.1. That's also representing what the slope is. Here, there's a y value of 1. That's also representing what the slope is, a slope of 1. This is maybe a y value of 1.5, and that is also telling us what the slope is. So it's very unique for the exponential function, where the y value is also describing not only the ordered pair, the location, but it's also describing the slope at that point. Natural log of x has a derivative of 1 over x. So 1 over x is the f prime for natural log of x. So number 4, it says find the value of the derivative at a given point. So understand that if it's ever asking you for the value of a derivative, it's a two-step process. First, we have to build the slope formula, and then we can use that formula to pinpoint the exact steepness at that point. So here's our function. Our function is 3 natural log of x plus e to the x. We want to find the derivative first, and we're going to apply each derivative rule to each of my functions. So any coefficient is just going to hang out in front. Any coefficient is not going to get impacted by the derivative. It's like 3x squared, right? 3x squared's derivative is 6x. That 3 just hangs out in front. It doesn't go to 0 because it's attached to a variable. If the coefficient is by itself, if that constant is by itself, then it goes to 0. But if it's attached to a variable, it just hangs out in front. All right, so the 3 is going to stay. Natural log of x becomes what? 1 over x. So I'm just going to make that derivative substitution. And then the derivative for e to the x is just e to the x. That's nice, right? The derivative of, there's no need to memorize e to the x's derivative because it's just the same thing. So this is now my slope formula that will describe the slope behavior of whatever this graph looks like. Now I'm going to figure out what the steepness of this graph is at 5 using the slope, using the derivative function. So f prime of 5 is equal to 3/5 plus e to the 5th. So it's going to be some positive number, some relatively steep graph, steep point, because that e to the 5th, e is around 2.7, so you can imagine, this could be close to anywhere between like 60 to 80. It's a really already a pretty large number. All right, number 5, what is the slope of the line tangent to the graph of 2 natural log of x at point x equals 8? So slope of the tangent just means, whatever the graph looks like, what is the steepness at that point? So we're basically just going to find f prime of 8. There's another way of saying find f or find y prime of 8. So first things first, we need to find the derivative. Natural log of x becomes, the coefficient stays. Natural log of x gets transformed. Here's our slope formula. Here's our slope or derivative at a point. So we can say y prime of 8. That means we're going to insert 8 into the derivative, find the exact steepness of this graph at this point. So the steepness of this graph at x equals 8 is going to be a pretty gradual positive slope of 1/4. And that makes sense. If you think about 2 natural log of x, natural log of x is going to quickly get very gradual in terms of the slope. So if they're all the way over at 8, you can convince yourself that it's not going to be a very steep slope, but it's still going to remain positive. Okay, you want to try number 6? Oh, I do want to point something out here. What is this E? What is that? What is that in relation to this problem here? That's just a what? Constant, right? So keep that in mind. E is just a number. Okay, so find the derivative and then plug 1 into the derivative to find the steepness of that point on this particular curve. So my f prime is 4 times 1 over x. We know e to the x is just going to stay e to the x, so that 3 hangs out in front. You know e is just a constant. That constant goes to 0. So we clean up f prime, plug 1 into f prime. I get 4 minus 3e. All right, page 19. All right, cosine and sine. We're going to explore the other 4 trig functions later, but these are the most important ones. These are the ones that show up the most often. So sine's derivative is simply cosine of x. So the cosine graph is going to describe the slope pattern of the sine graph. And cosine's derivative is negative sine of x. So if you were to look at the negative sine of x graph, every point on the negative sine of x graph is going to describe the slope behavior of the original cosine graph. So they're basically each other, just with a slight adjustment. Cosine is negative sine and not positive sine. Okay, see if you guys can try example before. Yeah, go ahead and try this example. See if you can find the derivative using the rules that's established. Right, everybody good here? 2 sine x becomes 2 cosine x. Cosine x becomes a negative sine x. The 2 negatives becomes positive. So this derivative is describing how the slope is changing on this original graph, whatever this graph looks like. Okay, try 13. You guys know the rule for e to the x. You guys know the derivative rule for sine of x. Find the derivative, plug in 0, and see what you can do to clean that up. e to the 0 is 1, cosine of 0 is 1. We're able to combine those constants, make it 4 plus 5 equals 9. Okay, try 14. Okay, questions up to 14. Okay, so 15 and 16, you're going to find the equation of the tangent line. So use the x value to find your order pair, and then build the derivative. Use the x value to find the slope at that point. And after that, you can put in the point slope form. You can leave it in point slope form for both 15 and 16. Okay, try that. See if you can use the order pair to get your, use the x value to get your order pair. Your derivative is where you find your slope. Once you have your order pair and your slope, get into point slope form. You can decide that you want to clean up past point slope form, but just want to keep reminding us that if you leave something in point slope form, college board will give you full credit. So basically, basically any variation of. But the reason that we stress point slope form is because it's the fastest, the most efficient one to get to. It's faster than getting to general form. It's faster than slope intercept form. So that's why we stress point slope form. Not because it's better than the other. It's just one that's quickest. So I found my derivative first. Cosine becomes negative sine. X becomes 1. Plugged in power 2. I got my slope. I went back and found my order pair. Use unit circle values to help me get it down to a single number. So I take my order pair, take my point, take my slope, point slope form. this time. Oh, sorry, it should be 5/2. Is that both x and y values are 5/2, right? So yes, I'm sorry. What you guys got? $16. I found my derivative first. Really doesn't matter which one you find first, but we just know we have to gather both sets of information, right? We need the y value and we need the slope. E to the x stays e to the x, sine becomes cosine, x squared becomes 2x. 0 is going to clean a lot of things up for us. We get slope of 1, order pair of 0, 4, 0, 4. And I stall for y, but you can leave it in any of those variations. Those are all fine. You leave it in point slope form. Okay, any questions? Okay, I'd like for us to start on page 20. Part of your homework, but I want us to try this. And then I will kind of go through each problem with you, but I want you guys to try these first. Okay, so let's start with page 20, number 1. Good. Number 1 is pretty straightforward, right? Okay, number 2, the line x plus y equals k, where k is constant, is a tangent line to the graph of y equals x squared minus 5x plus 2. What is the value of k? So I want to kind of give you some visual connection to this function or to what the problem is dealing with. So let's say you have a function that's x squared minus 5x plus 2, some parabola, right? And the key word here is that we know a line is is tangent to the graph of this f of x. So let's say the line was something like this, right? Is tangent to the graph at that point. Now, tangent means that there's something special about that tangent word there. It means that this line is going to share something with this graph, right? What is it going to share with the extended line in the graph? It's going to share what? It shares point, and it shares something else. Slope. Yeah, shares point and shares slope. And we want to use that knowledge to help us piece things together, right? And that sometimes the fact that they share an order pair can help us move forward. Sometimes the fact that they share the same slope can move us forward. So the strategy is that we're going to find the slope of this line, find the slope of the derivative function, we'll find the derivative function, and then if we set them equal to each other, we can find the location where they're going to, where we can establish that relationship, right? We know that they must share the same slope, and x plus y equals k, we can actually solve, we can get this and figure out what the slope is, right? If I solve for y, I can figure out what that slope is. And if it's tangent, that means this f prime must also have a slope of a slope that we're going to find. And if we can use that to solve for x, if we can solve for x, we can work backwards to solve for k. So x plus y equals k. If I solve for y, that's going to give me y equals -1x plus k. So we know that the slope of this line is -1. So this entire line is going to have a slope of -1. We can match that with f prime because we know that f prime is going to describe the slope behavior of my original curve, x squared minus 5x plus 2. And this is really helpful because we can use f prime both ways. You can give it an x value and ask for the slope. We can also go the other direction. You can give it a slope and ask for the location where that's going to occur. So we can use that to our advantage because we know what slope we're after. We're after a slope of -1. And if we solve for x, we can find the location on the graph. Okay, it's not drawn very accurately here, but we can find the location on the curve where these points are going to meet. And if I know that the equation, these two graphs will share the same point at x equals 2, I can go back to my original equation and set these equal to each other and replace x with 2, and that's going to give me an entry point to solve for k. I can find out like this. So I can set both equations equal to each other. If I solve for y for the line y equals -x plus k, f of x is x squared minus 5x plus 2. I set them equal to each other, and then now I'm just off to trying to solve for k. Some of these problems are referencing things I haven't quite gone over yet. If f is my function and f prime is my derivative, there's also a real world application to this. If x is my position function, then x prime is the rate of change of position, which is going to be relating to velocity. So an object moves along the x-axis so that its position at time t is x of t equals 3t squared minus 9t plus 7. At what time is the velocity of the object equal to 0? So basically another way of saying, if my function is this, when is my slope going to be equal to 0? So likewise, we're just translating into a different scenario, and we're using position and velocity instead of function and derivative, or any function and f prime. So velocity is the rate of change of position. So velocity is the derivative of position. So I can just find my velocity function going through power rule. So any t value I plug in, I can find the velocity. Any velocity I plug in, I can come back around and find the time that it occurs. So I'm looking for a velocity 0. So I'm going to use my velocity function to work backwards and find the time when this object is going to reach that velocity of 0, and that's just solve it. We use x as a variable for position because usually a lot of times these problems are moving along the x-axis. So position along the x-axis, that's why x of t is used, or x is used for position. Number 4, we find f prime. We plug 3 into f prime. We get that number, and then we substitute that in for that where the f prime of 3 is. And natural log of e to the 3. You know, natural log and exponential e to the x are going to cancel each other out. The only thing left is going to be that 3. Number 5, equation of a normal line. So again, normal line means perpendicular. So our strategy is let's find f prime. Let's find f prime negative 2. Figure out what that slope is at that point, and then make the adjustment, create the slope that is perpendicular to it, which is opposite reciprocal. And then find the location of at that point. You can plug negative 2 into the original function, get the y value. Once you have your order pair and your slope, you can put in the point slope form. And then it looks like your answer choice A through D is in general form. So take your slope intercept form and then rearrange it and get the x and y together and see if you can match the correct answer choice. I just want to see if we can get through 6 before we stop. So go ahead and keep going till we finish 6. Yeah, number 6 is, you see that word tangent. So we know that that line and that graph is going to not only share the same points, they're also going to share the same slope. So we can find the slope of the line. We can build a derivative, which is the slope of the curve, set them equal to each other, set the slope of the line equal to the slope of the curve. And then that can give us an entry point into solving for the variable that we want to solve. So after you set your derivative equal to the slope of the line is going to end up being 9/16, because if I get into y equals mx plus b, I can see that the coefficient in front of my x is my slope. So once I have my slope from the line, I can set that equal to the derivative of my function. I can work backwards, solve for x. Once I solve for x, I'm still not ready to plug into my original function to solve for k, because I still need my y value. So I'm going to take that x value, plug it into the original function to get the y value, because we know they're going to share the same point. So if I can find the x and y value from the linear graph, I can use both the x and y value to now figure out what the k value is that I'm looking for from the curve. And so it's nice that we're getting exposure to these multiple choice questions, because these are, the types of problems that we want to be able to kind of eventually work towards, kind of giving you a taste as to what an AP exam multiple choice question can feel like. It's usually multiple steps. It's usually not just, oh, find the derivative of 2x squared. Usually it's multiple steps leading into a problem. All right, so check your calendar for the rest of your homework. Tomorrow, we will do product rule and quotient rule. All right, come get your phones.